Now that we've come this far in the topic of probability, it is always best to regroup and list down the subtopics and concepts we have taken up so far. I've already talked about classical and relative frequency probabilities and contrasted it with subjective probability. I've also extensively defined marginal and conditional probabilities, as well as joint probability and how it relates to the multiplication rule. And finally, we've tackled and differentiated dependent from independent events. Now that we've got that out of the way, we again come back to the same contingency table we've been using since the beginning of this video. Now, suppose a patient is randomly selected from the total group. What is the probability that this patient will be from the eplerenone group or the placebo group? Again, pay close attention to how the question was constructed, and take note of the conjunction OR. Now, the probability that we are interested in here has this particular notation, and this is read as the probability of the union of E and L, or the probability of E or L occurring jointly. What it all comes down to is that we want to add the marginal probabilities of the eplerenone group and the placebo group together. The marginal totals for the eplerenone group and the placebo group are 1,360 and 1,369 respectively. And since the selection will be made from the total set of patients, the denominator for each probability is 2,729. Now, adding these marginal probabilities together, we get an overall probability equal to 1. Thus, when we select a patient at random from this group of 2,729 patients, we are absolutely certain that this patient will belong to either the placebo group or the eplerenone group. Now, as we mentioned a few times in this video, patients enrolled in this clinical trial who satisfied inclusion criteria are randomized to be either in the eplerenone group or the placebo group. So it is expected that these patients, or rather the patients in the placebo group, did not receive any eplerenone, and those in the eplerenone group did not receive any placebo. Thus, we assume these two treatment groups to be mutually exclusive. But what is mutual exclusivity anyway? Two or more events are said to be mutually exclusive if the occurrence of one precludes the occurrence of the others. In other words, if two or more groups are said to be mutually exclusive, one member of one group should not be a member of the other group or groups at the same time. In our case, a patient cannot be on the eplerenone group and the placebo group at the same time, or else it be some major protocol violation. Now, when two events, A and B, are mutually exclusive, the probability that A or B will occur is the sum of the probability of each event. This is what's called the addition rule. So, if we are to construct a Venn diagram for this here would represent the complete set or the universe, which has the 2,729 patients to which we have data on adverse events. This portion here would be the eplerenone group, consisting of 1,360 patients, and the rest of the sample space would be the placebo group, consisting of 1,369 patients. The union of these two groups will then actually be the whole set of 2,729 patients. Note that there is no overlap whatsoever, which points to the mutual exclusivity of the two groups. Similarly, the probability of the eplerenone group is complementary to that of the placebo group. I will be defining what complementary events are in a bit. But before that, what if the events are not mutually exclusive? We go back to our table here. Let's now look at the treatment group assignments as a whole and the occurrence of hyperkalemia. Treatment group assignment and the occurrence of hyperkalemia are non-mutually exclusive events because the occurrence of one does not preclude the occurrence of the other. From the table, the probability of being in the eplerenone group is 1,360 over 2,729, or 0.4984. And the probability of having hyperkalemia, which we will designate as K, is 159 over 2,729, or 0.0583. The probability of being in the eplerenone group or of having hyperkalemia occurring jointly is not at all equal to the sum of these two probabilities. If you are to use the addition rule from earlier, you will notice that the patients in the eplerenone group with hyperkalemia will be counted twice. If you are unable to visualize this, hopefully the explanation using a Venn diagram will make things clearer. We again have here the complete set or the universe, which has the 2,729 patients to which we have data on adverse events. We then let this circle here represent the patients who were randomized to the eplerenone treatment arm. Now this other circle here would then be for the 159 patients who developed hyperkalemia during the course of the study. Take note these two circles overlap each other, and this overlap will actually be counted twice if we use the addition rule formula. We must now devise a way to modify this addition rule so that the overlap or the intersection is not counted twice, like so. This then would be that modification to the addition rule. Given two events A and B, the probability that event A or event B or both occur is equal to the probability that event A occurs plus the probability that event B occurs minus the probability that the events occur simultaneously. So going back to our Venn diagram, if we add the probability of event E and the probability of event K together, the overlap, which is the probability of the intersection of E and K, will be unintentionally counted twice. By subtracting that value from the sum, we now get the correct joint probability of either event E or event K occurring. Now, as promised, I'll be talking briefly about complementary events. There's really nothing much to it except that there are two mutually exclusive outcomes of an event that are the only two possible outcomes, and the sum of their probabilities will be 1. Expressed mathematically, we have this. A bar here on the right side of the equation represents the complement of A. If you subtract its probability from 1, you get the probability of event A. Going back to our Venn diagram, we see that as far as the event of treatment group assignment is concerned, there are only two mutually exclusive outcomes to this, namely being in the eplerenone group and being in the placebo group. If you add their two probabilities together, we get the sum of 1. So we're almost done with this video series on the fundamentals of probability. Now that we're familiar with the different types of probability, I would like to finish this off with what are called the axioms of probability. So for those who are not familiar with the term, an axiom is a statement that is regarded as being established, accepted, or self-evidently true, and therefore they are not susceptible to proof or disproof. Now, there are actually three axioms of probability. It was the Russian mathematician Andrei Kolmogorov who formulated these axioms. The first axiom states that the probability of an event is a non-negative number. The smallest probability that can be is 0, and the largest probability that can be is 1. And it can never be negative or infinite. But of course, there are infinite possibilities between 0 and 1. The second axiom states that the probability of all the events in the entire sample space or universe is 1. As far as the experiment we used as example is concerned, we limit ourselves only to our appropriate sample space, which is the 2,729 patients with which we have data on adverse events. Now, this sample space contains all the possibilities for this experiment, and any events outside this sample space is non-existent as far as this experiment is concerned. Now, to explain the third axiom, recall the addition rule formula. For two events that are mutually exclusive, so take note, mutually exclusive, the union of their respective probabilities is equal to the sum of these same probabilities. Now, in a sample set, there may not just be two mutually exclusive events. There could be 3, 4, 5, 10, 50, 100, well, several events, even an infinite number of events. Nonetheless, the union of these possibilities, or rather the union of the probabilities of all these mutually exclusive events is equal to the sum of the probabilities of all these events in a sample space. Now, you may have encountered the mathematical notation that you see at the far bottom of this slide, so don't be intimidated by it. It basically just says that for a sample space that has an infinite number of mutually exclusive events, the union of the probabilities of all these events is basically equal to the sum of the probabilities of all of these events.